Hi, I'm Dan Howe with LMI Technologies. I want to give you a demonstration of the Gocator 2300 series laser line profiler, which is a 3D smart camera for 3D measurement and control for factory environments. Now, the laser line profiler is a product from our smart 3D sensor families, and this particular line profiler has a 1.3 megapixel imager in it and gets high resolution, high speed scans for profiling and for surface generation. This particular model, the Gocator 2330, has a laser line generator in it and a camera, as well as a full processor on board for complete tool set to allow a user to craft their own applications on board and do measurement and control in a factory environment. So let's get started. We're going to set up a gantry and start scanning. Okay, so we've got the sensor mounted to the gantry at a position where the proper standoff is set up to the far end of the measurement range. And on the gantry we've got some wheels, including this wheel having an encoder on it so that we can track our motion when we do scanning. It's connected through a small connection device and Ethernet into my laptop here. One great thing about the Gocator is that you don't need any separate software to program it. It works off of a browser-based software, so any standard browser would allow you to set up your Gocator. So let's get started. Okay, so we've mounted the sensor on the gantry, we've assembled the gantry, and now we're ready to start scanning. I've got a browser window open. In this case, I've got Firefox open, and we just need to open up a new tab. And I'm going to put in the IP address of the sensor, which is a standard IP address that we ship it with. Users can change that IP address to whatever they like. And here's the login screen. Once inside the user interface, I have a number of screens to go through in chronological order. This is the manage screen where the users can change their IP addresses, set passwords. We have areas where you set up job files, save job files, as well as upgrade firmware, things like that. Then there's the scan screen. The scan screen is a screen where the users can optimize the scan, change exposure, change speeds, things like that to get profile scans. There's a model screen, which is for pattern matching when needed, and a measure screen. So once the scans are optimized, the users can then now use the measure screen to create profile tools and surface mode tools. An output configuration screen, so once the tools are created, then the users can decide how they want to output those tools to their control system. And finally, a dashboard. The dashboard is a screen where you can see health statistics of the sensor as well as the measurements that you've created and monitor those. So we're going to move back to the scan screen and turn on the sensor. You can see the laser line here. And I'm just going to put my fingers in there and we're looking at a live scan. Right now we're measuring this 200 times a second. We are scanning. So we get over 200 profiles per second. Users can increase that speed. And in each one of these profiles we get over 1,200 points. So we're actually generating somewhere around 250,000 points per second. Okay, so let's scan an actual object. I'm just going to put this wood block in there under the laser and we'll look at that profile. And if I zoom in, you'll see that this profile is made up of individual points. And if I zoom in here, you can see those points. They are separated with this particular model by 44 microns, which is the X resolution of this Gocator 2330. And you can see if I zoom very, very far in, those points are kind of moving around. That is within the noise band of the sensor, which is, in this case, about 10 microns. If I zoom back out, you'll see this whole coordinate system is part of our factory calibration. So on the x-axis is our x dimensions, goes from about 0 to plus 40 or so, and down to negative 40. That's our field of view in this case, which is about 85 millimeters. And the y-axis here is actually our z or z height plot, and this goes from minus 40 to plus 40. That's the measurement range of the sensor. You'll see that as I zoom in here, this is the profile. This profile is actually created by the image of the returned light to the camera. If I go into a video mode, you will see the actual image on the camera. This is how we determine the Z positions of the points. These sensors are mapped out in a factory calibration process. And if I zoom in here, you'll see the returned light on the various pixels of the camera. We actually calculate at each point the center of gravity of light. So if I show those spots, you can see the actual calculated spots. These are done by a very sophisticated process that gets sub-pixel to produce the Z height maps for each profile. So I'm going to go back here into the profile mode, and you'll see that because of the way the sensor is mounted, I have the table, and in this case also the block, kind of at the far end of the field of view of the sensor so that I can have enough room to have different targets of different heights and scan those. If I really want to align this, so if this was mounted above a conveyor system and I wanted that conveyor to be mounted to be at the 0 level, I would just do a very simple alignment to that conveyor, to that machine coordinate system. So we have a coordinate system in X and Z, and we can align it to whatever coordinate system the machine is. So to do that, we have a very simple process. In this case, I'm doing an alignment to a flat surface. We're going to use the table. And what it's going to do is we're going to do a quick line fit to the table and correct for any tilt and also set Z and X offsets as needed. So if I click the line button, we will see that we've now straightened out the profile, flattened it, and we've set the table at 0. Basically what it did is it went in here into this transformation function and populated these values automatically. So I am now aligned. Now what you didn't really see is that it did correct for any angle variance, but because this is mounted so that the angle is basically 0, you didn't really see that very well. So I'm going to clear this alignment really quickly, and I am going to just kind of exacerbate a tilt angle. Maybe I have to mount this sensor in a way where there's some sort of obstruction and I have to come in on an angle. That's fine as long as we correct for that tilt. So I've just kind of created a large tilt here, and I am going to realign. And as you'll see, I'm now corrected for that fairly extreme tilt, and I can measure objects even with that tilt. And basically this transformation function now contains about an 8 or 9 degree tilt correction. And so this could be a very extreme, 20, 30, 40 degrees if needed. Sometimes we use 2 sensors together, and in that case you might have a sensor coming in from one angle and from another angle, and you might have different angle corrections for either to recreate that in a global coordinate system. Okay, so let's put this wood block back in, and actually before that we're going to just realign to the table. So I'll use this alignment function again, and so we're aligning to the flat surface of the table. And now I'm going to put this block in. We're actually going to make some measurements now. So in this scan screen we can actually change a lot of the parameters. So currently I'm going 200 profiles per second, but we can increase that. We increase that by either windowing or subsampling, and I can show you that a little bit later. Right now 200 hertz profile rate is just fine. We can also change exposure. There's various exposure methods that if the targets are of different colors or different reflectivities, we can modify exposure to optimize the scan. Currently the default exposure of 400 microseconds is just fine. We can also do some profile filtering, which I don't really need to do here, but I can filter this profile to improve the results as I see fit. But this current profile we have on the block is just fine. We're going to use this and go to the measure screen. And so I am in what's called the profile mode. So in the profile mode I have a tool set for what we call profile tools, and there's a drop-down menu. I can choose a wide array of tools. In this case, let's create a block height tool. So this is going to be a tool that measures the height of this block relative to some datum, and this datum in this case is going to be the table. So I'll select the profile dimension tool, add that tool, and now you'll see I have 2 feature boxes, feature box 1, F1, and feature box 2, F2. We're going to get the relative height difference between these 2 features. So feature box 1, we're just going to change its size. We're going to drag it over here to the table, and in that feature box, first of all I'm going to select height. in this tool. And in that feature, I can pick in this region of interest that I've selected the maximum Z, the minimum Z, the average Z. In this case, it makes sense to just take the average. We're getting a number of points across this, this feature box size, and we're going to average that. And then feature box 2 will do the same thing, but we will drag this on the top of the block, and we will take the average, the average of that. So we have average height of the block and the table, and we're getting a value of 15.175. That's in millimeters, because this is a factory calibrated device. So we're down to the micron precision level. This sensor is good to about 10 microns resolution, but we actually report our value down to a micron. And here I'm creating that value. I can also determine if this is within some sort of acceptable range. So I can go to this output configuration and say, I need to be between, say, 14.5 and 15.5 millimeters. So I'll put in a minimum and a maximum acceptance. And you'll see that that number turned green means we're in the acceptable range. If for some reason this block was a bit thicker, higher, you'll see I fall out of that range and it turns red. So if that's all I wanted to do, I could go right to my output screen and say, well, gee, what do I want to do with this height output that I just created? I can deliver that in a variety of ways. We have an Ethernet output. We have this Ethernet output is actually our own Gocator protocol packet structure. You can get the entire profile as well as the tools that you create. We have PLC protocols, Modbus, Ethernet IP. We have an ASCII protocol, RS-232 serial. You can scale an analog output, and we even have the discrete digital outputs. Because I created that pass-fail, we can send that out as a discrete digital good or bad type output. So let's go back and create some more tools, because this is really one tool measuring the dimension of the height. But let's say I also want to measure something like width, so we can create many tools that work simultaneously. You'll see up at the top there is a CPU percentage. Right now it's at 17%. This is the processor on board the sensor, and I just have to monitor that. There's plenty of CPU power, but as I create tools or I change the speed of my sensor, that number may rise, and I have to just monitor that. And once I start to get up near 100%, that's starting to hit the limit of the processing capability on board the sensor. Now LMI has a new feature coming out soon called the Accelerator, Go Accelerator, which allows users to offload processing to a PC-based environment, which will allow more processing. So if you have a limitation of the sensor processing, you can augment processing by using a computer to do that. So let's create a width tool as well. So I've got this height tool. I can actually name this tool what I want. So we're going to call it block height. And we're going to create a second tool. So I'm going to go back, create profile dimension, and I'm going to add another tool. And I'm going to call this one block width. So I'll type in block width. And for this tool, we'll use these same feature boxes, but we will put one on the left side. And in this case, I will grab the min X, so that'll be the far left point. And in the feature box 2, I'll drag it near the right side, and I'll use max X as the feature. So you can see now I'm measuring the width of the block. You'll also notice I don't see the sides of the block, and the reason I don't see the sides of the block is that I have a fanned laser, and it creates shadows there. That's what we call occlusion. So we can't quite see the sides of the block unless I use two sensors coming in from angles, what we call a buddy system, and we have capabilities inside the sensor to allow users to connect two sensors. But in this case, with a single sensor, I won't see the sides of the block, but I can see the corners here and measure the width. So here I've got a width of 29.612 millimeters. Again, similarly, I can put in pass-fail criteria, so I'll say I need to be between, say, 29 and 30, and that turns green. And so now these two tools are measuring. We have the height measurement, 15.152, and the width measurement, 29.612. And if I go back into my output screen, you'll see these two values show up where I can include those in my output, whether it's in the GoCater Ethernet output, or if I go into the Ethernet IP PLC outputs, there is a map here showing the registry number and where to grab those values. I can choose to grab the actual measurement values in millimeters, and I can grab the decisions as needed. Okay, so I'm going to create one other tool, and I want to explain a thing about aspect ratio. As I mentioned, these sensors are factory calibrated, which means that the cameras are mapped, the pixels are mapped through our calibration process so that we know where every pixel is in real world coordinates. So in my measurement tool, I have block width, I have block height. But one of the nice things is the fact that because we are measuring profiles, that we can correct for tilt in that profile. So I'm measuring the block width, but if I tilt this block, you will see basically we're only going to measure the x to x width, which means tilt will actually reduce the value. So if I want, instead of having a width measurement, I can use what's called a distance. And this distance tool will actually incorporate the tilt into that measurement and keep it correct. That's one of the nice things about measuring in 3D versus 2D. So with 2D vision, if I were to measure the block of this, I could potentially measure the width of this block with a 2D camera. However, I would have issues with aspect ratio. And so if I raise these feature boxes up, what you'll see is that my width will not change as I get near the sensor or get near the near field area. We're going to maintain that distance measurement. If I were using a traditional 2D camera, we would actually measure a greater width in the near field than we would in the far field, just based on aspect ratio. Otherwise, you'd need something like a telecentric lens. So the distance measurement and the fact that we have a factory calibrated environment means that we can measure that width distance no matter where we are in the field of view. One thing that you might have a problem with is if you were trying to measure the width of this block and for some reason you didn't quite know where that block was. Let's say these were coming down a conveyor and the block might be in the center of the conveyor, maybe it's on the left side or the right side. These tools that I've created, these feature boxes, may not be in the correct spot. And that's why we have a very easy to use anchoring system. So what I can do is any tool that I create can be used as an anchor. So I'm going to create a tool called Profile Position, and I'm going to create this for the specific purpose of creating an anchor. And in this case, we are going to rename this tool, and we're going to call it Anchor. And in this tool, I have one feature box. And with that feature box, I am going to pick a feature that I want to use as my anchor. In this case, I'm going to select an X position, and I'm going to select min X. This means that the far left side of this object will be used as an anchor to anchor all the other tools to for my width and height measurement. So if I select this, I've created a tool basically that has an X output. In this case, it's minus 13.2 millimeters or so. This is actually the location within our coordinate system of where this is. So if I move this around, you'll see I'm at 0, I'm at plus. It's just tracking the edge of the object. If I go in, if I create that tool and I go into, say, my block width, I can now select the anchoring tab and anchor that tool. Right now, that currently the X anchor is disabled, but if I enable it and select the anchor X, which is the X value of the anchor tool that I just created, I've now anchored that tool so that it will track, the feature boxes will move with the edge of the object. Meaning, if I have this block of wood and it comes in on the right side, these feature boxes will find it. And if it's on the left side, they'll find it as well. This also works for the height tool. So if I go to that tool, I can also anchor that tool to the X anchor. So now both tools are anchored. Now these are just anchored in X. We can also anchor in Z. So if I go back to that anchor and I create a Z value, so now it's using that same position tool to create a Z value. Again, we're going to use the left edge, which is just fine. And now I can go into the block width and also anchor it in Z. So I'm X anchoring it and Z anchoring it, so I can actually move this block anywhere within the region of interest and measure its parameters, measure its width and its height.